This is part two of chapter 8 for error correcting codes for modern communications. So previously we talked about block codes, specifically linear systematic block codes, and how to construct them, how to construct generator matrices, and how to construct parity check matrices, and then how to interpret the use of those. So now we're going to talk about convolutional codes. So skipping on to convolutional codes, uh, the idea of a convolutional code is basically we have a structure. When we pass information bits into the structure, it has memory of previous bits that came in some fashion, and we then generate uh, functionally output bits. Here we have two examples. We have a recursive systematic block code, and we have a non-recursive non-systematic block code. You could have those in any combination you like. In particular, in this case, what we have is we have uh, input bits flow in from the left, and for each bit, we get multiple output bits. In this particular case, we have constructed this so that for an input bit, we get two output bits. So every input bit comes in, every information bit that comes in, we get two output bits. In the example on the left, you can see that one of the lines is basically not affected at all. And so it's a systematic code because every information bit is directly exposed. You can see that information bit. And then we have this sort of complicated diagram that produces another bit. And that complicated diagram is built out of summing bits or exclusive ORs, if you like, and a shift register. So a shift register is basically memory that each clock cycle it takes all those memory bits and shifts them over by one spot. So we'll write this down, and then we'll often refer to this a particular sequence of entries in that memory as a state. And so each time the clock ticks over, the last position is thrown away, and the one before it is moved into the last position, and the one before that is moved into the one that's ahead of that. So in particular, in this case, whatever is in S3 is thrown away. S2 is moved into S3. S1 is moved into S2. And then whatever the input of S1 is becomes the new S1. So the convolutional code structure on the left, once again, is a systematic convolutional code. It's also recursive. And the reason why we say it's recursive is that the next bit of information that goes into that shift register is a function of stuff that comes from the output. So there's stuff that comes from the output and gets fed back. Stuff gets fed back. That's a function of the state, and plus the new input bit. So it means it's kind of messy. And so it's recursive because stuff is being fed back. On the right, what we have is a non-systematic, non-recursive convolutional code. And we say it's non-recursive because uh, the the information which sets what the states are going to be, there's nothing feeding back changing that. So the states are just basically a memory of previous input bits. Once again, each sort of clock clock cycle that goes off, whatever is in S3 is thrown out. Whatever is in S2 moves to S3. Whatever is in S1 moves to S2. And that previous sort of information bit gets moved into S1. So if you think about how much memory we have here, we have in this particular example, we have three previous information bits or three blocks of information that's some function of the previous information bits, plus the current one. And so we say this is a constraint length 4 convolutional code because it has 3 memory bits plus the current one. So that's we refer to this as a constraint length 4 code. And because one bit goes to 2 output bits, we say it's a rate 1/2 code. I will say that constraint length codes are 4 particularly weak, so this is not a common structure, but it's useful to keep them small so we can talk about them. Constraint length 7 to as much as 11 are used in commonly. And I think I mentioned this before, is sometimes people use higher order Galois fields in this as well. In any case, what we have here is a example of a recursive systematic constraint length 4 rate 1/2 convolutional code and a non-recursive non-systematic constraint length 4 rate 1/2 convolutional code, and both these are just operating on a GF2 or binary. All right. So let's, for the sake of our sanity, play with an even simpler non-recursive code. Once again, real ones are much more complicated, or ones that people really use are much more complicated, but we'll keep this fairly simple so that we can actually, on a slide, go through the structure. So there are 3 different representations here. Arguably, there's also another representation that you could construct too, which is more mathematical. But we have that sort of block diagram structure. We have a table down below that. And to the left, we have something we call the trellis code. Now, they all basically have the same information in them. There's 3 different ways of representing the same thing. All right. So often, as a practical matter, if somebody hands you the block diagram up above, the first thing you would do is build the table out below it. And from the table, we would construct the trellis. All right. So let's walk through doing this. Well, for this non-recursive convolutional code, we know that the input is either a 0 or a 1. So we can always say the input's a 0 or 1. We have what we sometimes refer to as the state of the shift register. So this case, it's a super short convolutional code with constraint length 3, which means there are 2 memory entries in the shift register. And so the possible states of the shift register, we can just enumerate them all. In this case, they could be S1 equals 0, S2 equals 0. So that's the 0, 0 state. S1 is equal to 0, S2 is equal to 1. So that's a 0, 1 state. They could be the 1, 0 state and the 1, 1 state. So we have the S1, S2. For historical reasons, people often put a slash between them, but it's not divide. So we got the 0, 0, 0, 1, 1, 0, 1, 1 state, right? There are 2 entries in the shift register, so there are 4 possible states. Had there been 3, there'd be 8. Had there been 4, there'd been 16, so forth. So we also know in this case, because it's a non-recursive code, that the what's in S2 gets thrown away on the next clock cycle. What's in S1 moves to S2, and what's the input bit moves to S1. So we can also write down what the next state's going to be. So if we start with the 0, 0 state, and the input bit's is 0, then we get the 0, 0 state again. If we start with the 0, 0 state, and the input bit is a 1, we get a 1, 0 state for the next for the next transition, and so forth, right? We can immediately write down whatever the current state is. We can write down the next state immediately, and this is sort of independent of the structure as long as we know it's a non-recursive code. All right, so then we have to figure out what the outputs are. It's very common to get confused between the memory states, which we are sort of strangely focusing on here, right? So this is something different from the other way we thought about codes, and the outputs. So remember, the receiver is going to see the outputs or maybe some corrupted version of the outputs. Um, but they're dependent upon what the memory states are. So let's just work out what the outputs are. So if we have the 0, 0 state, and typically, by the way, when you start using convolutional code by convention, you assume that you're starting in the 0, 0 state, but you could pick any state you want. So long as the transmitter and receiver agree, it doesn't really matter. But let's assume we're always going to start in the 0, 0 state. Then if we had the new information bit is a 0, then basically everything is 0. The shift register is full of zeros and the input 0. So if we then go along the top path in our block diagram, the S1 is the output of that we see is a 0. The input's a 0, so 0 plus 0 is 0. S2 is 0, so 0 plus 0 is 0. So C1 is 0. Along the bottom path, S1 is 0, and the input is 0. So 0 plus 0 is 0, and so C2, the output C2, is also 0. So if we start with state 0, 0, when we have a new input bit or an information bit of 0, then the output, what is actually sent out and is going to go through the transmitter, is 0, 0. Well, that's pretty boring. Now let's say the information bit is 1. So we're starting with state 0, 0. Information bit is 1. So output of shift register in position 1 is a 0, but the input is a 1. So 0 plus 1 is 1. S2 is also 0, but we have a 1 going along the upper path. So 1 plus 0 is 1. So now C1 is 1. Similarly, along the bottom path, S1 is 0, but the input bit is 1. So 0 plus 1 is 1. Output C2 is also 1. So you can see along the what is the second partial row started with state 1, 1, had an input of 1. And so now the output bits are 1, 1. So we can do this with all possible scenarios, right? So let's just pick one for fun. Let's say we have state 1, 0. So that's the third block of states. And let's say that the input bit is a 0. All right, so S1 is 1 and S2 is 0 in this case. And so if we follow the top path, S1 is 1. All right, well, there's a 1 up there. And then input bit is a 0. So 1 plus 0 is 1. State 2 is a 0. Sorry, the second memory block is 0. But we have a 1 coming into it, so 1 plus 0 is 1. So output is 1. Similarly, we go memory S1 is 1. Input is 0. 1 plus 0 is 1. So output C2 is also a 1. So we put in a 0 as our new bit, but we got 1, 1 as the output, which amusingly is the same as we got before when we had 0, 0 as the state, and we put 1 in as the input, and we got 1, 1 as the output. So in both those scenarios, we get 1, 1 as the output, but they're clearly a very different situation. So what we end up leveraging to decode is the fact that we know there are a limited number of state transitions, and that ends up being key in making this all work. All right, so now we have calculated all the entries in this table. We have all the input bits, all possible state transitions, and for every state, you have the possible input bits, and then that gives you all possible output sequences as a function of the state and the input. And maybe just to clarify, you go and calculate this based on the current memory, and then the clock ticks, and then you throw away S2, move S1 to S2, and move the input into there. And a new input bit comes in, and then you calculate this again. So you're marching along. So now we can take this table, and theoretically, if somebody handed you the table, you could build up the block diagram, although for a complicated convolutional code, it's a little tricky. But in theory, you could. But you can build this other diagram on the left here, which we call the trellis. So what the trellis focuses on in some extent is the state transitions. And the reason why it focuses on that is that not all state transitions are allowed. So what you see on the left-hand side are the four possible states. And on the right-hand side, those are also the four possible states. So along the first row, it's state 0, 0 on the left and state 0, 0 on the right. So we know that because of the way this thing works, that we can potentially transition if the input is a 0 from the 0, 0 memory state to the 0, 0 memory state. If the input bit is a 1, we can transition from the 0, 0 memory state to the 1, 0 memory state. So that's the arrow going down diagonally. So we just, for the sake of notation, we say that we have an input information bit, which is the 0, and that gives us a state transition to 0, 0 across the top line. It also gives us an output sequence of 0, 0. So remember, the state transitions are the structure of the code. The output bits are what the receiver theoretically should see, but it might be corrupted. And so we can go from each part of the table here. So we can go to the 0, look at the table and say the 0, 0 state. Starting at the 0, 0 state, I could go to the 0, 0 state or go to the 1, 0 state. So I draw those two arrows. I can go to the next state, the 0, 1 state. I can go from the 0, 1 state to the 0, 0 state or the 1, 0 state. Draw those two transitions. And the 1, 0 state, I can go from the 1, 0 state to the 0, 1 state or the 1, 1 state. Draw those two transitions on our trellis. And from the 1, 1 state, I can go from the 1, 1 state to the 0, 1 state or the 1, 1 state. So you notice that in some sense, half of these transitions, notionally are missing, right? And that's important because not all state transitions are allowed. That's the power of the code. All right. Also, along each one of these segments from vertex to vertex, right? There's an information bit and there's an output bit. So we will label those as well. So if you go along the top, from 0, 0 to 0, 0, along that top transition, we know that the input bit had to be a 0 and the output bits had to be 0, 0. And so we can label each one of those segments going from the vertices with what was the information bit that caused that transition and what are the output bits that are sent off to the receiver. We put those in the parentheses. And corresponding to C1 and C2 on the output. And so as we encode the data, it moves along these various transitions, and it kind of goes from state to state to state to state, depending on what the input bits are. And depending on what the input bits are and the state transition, that gives us what the output bits are. All right. So let's actually just sort of unwrap this trellis or do a whole bunch of basically put trellis next to trellis, next to trellis, next to trellis. And let's do this for a sequence of bits 1, 1, 0, 0, 1 as our input. All right. So what does the receiver know? The receiver knows that we start in the all 0 state. The receiver knows what the structure of the code is, what are allowed transitions. And the receiver knows that we're going to send 5 bits across. All right. but it doesn't know what path it took. It doesn't know what the information bits are. Well, let's start with thinking about what the encoding does. So this is at the transmitter side. All right, so by convention, we start in the 0, 0 state. And the first input bit is a 1. So if the first input bit is 1, then we transition from state 0, 0 to state 1, 0, right? And I've labeled that with b equals 1 there. And then, so now we're in state 1, 0. We get another 1. And if we're in state 1, 0, then we go down to the state 1, 1, and we get a 0, 0 on the output. So if you notice, I put the output sequences up along the top. All right. And then, so we're now in state 1, 1. And if we get our next input bit is a 0. And then under that condition, we transition to state 0, 1. All right. And we get output bits 0, 1. Once again, the output bits in this state are different things. So keep that clear, straight in your head. All right. So now we're in state 0, 1. And we have a input bit of 0. And when we go along that path, we transition to state 0, 0. And our output bits are 1, 0. So we're now in the state 0, 0 up top, and the last bit is a 1. And if then we're going to go along that transition, the information bit's a 1. That gives us a 1, 1 at the output. And we end up in state 1, 0. All right. So if all goes well and there were no errors, and the receiver would identify that the sequence was 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. And if there were no errors, it could just go, I can follow that back and figure out what the bits were that were the right bits. Problem is, the receiver doesn't know that there were no errors. In general, we have to assume that there's some errors in the that it saw. That is, instead of getting the output sequence of 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, some of those bits might have been flipped. And the error correcting code's job is to provide a structure and an approach for fixing those errors. So then the question is, how do we do that? And the somewhat amusing answer is the receiver explores all viable paths and figures out which one's the best one. As you might imagine, that's kind of an explosion of paths, particularly if our constraint length is fairly large, because then what happens is instead of having 2 to the 2, you might have 2 to the 7 or 8 or 9 states. And so you wouldn't even be able to see the dots because it'll be so closely packed together. And exploring all possible state transitions, even though not all of them are allowed, but all allowed state transitions to try to figure out what's going on is a lot. Fortunately, we have computers for that. Anyways, this is the reason why we picked a simple application or a simple convolutional code so we could walk through it. All right, so let's do that. And if you do that, what this is called is the Viterbi decoder. Viterbi observed that the right answer is to explore all possible sequences. All right. In our case here, what we're going to assume is that what the receiver should have observed was the output bit sequence 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. However, we're going to say that it actually observed a 1, 1, 0, 0, 1. That's a bit flip. 1, 1, 0, 1, 1. So there's a corrupted bit that came in. And now we're going to try to see if the Viterbi decoder, given our relatively weak error correcting code, can it fix it? Well, so how do we do this? We are simply going to walk through all allowed paths. So we know we start in the 0, 0 state. So we're starting in the upper left. Then there's a transition from the 0, 0 state potentially to the 0, 0 state, and from the 0, 0 state potentially to the 1, 0 state. Now we know that the going from 0, 0 to 1, 0 should be the right answer, but the receiver doesn't know this. So it writes them both down. And then what it does is it calculates the output sequence it should have seen going down each of these paths. What is the Hamming distance between that output sequence and what I actually observed? So if I observed a 1, 1, and I hypothesize that we went across the top path, then we should have gotten a 0, 0, right? We go over and look at the trellis on the left. If we went along that top path, we should have seen a 0, 0. We observed a 1, 1 in those output bits. So the Hamming distance between those two paths is, or between those two potential output sequences is, or the observed sequence and the output sequence that we should have had, is 2. On the other hand, we observed a 1, 1, and if we followed the state transition from 0, 0 to 1, 0, then we get a Hamming distance between the observed bits, the observed coded bits, and or potentially coded bits, and the coded bits going down that path of 0. Well, that's a good sign. However, we don't make any decisions. We're going to follow all possible paths. All right, so now we could be in state 0, 0 or state 1, 0. And from those two states, we now can potentially transition to all possible memory states, right? So we could follow the top path. We can go down from 0, 0 to 1, 0. If we happen to be in the 1, 0 state, we could follow that from the 1, 0 state to the 0, 1 state and the 1, 1 state. And therefore, we have now been able to potentially follow all paths. Now, do the same thing. We calculate the Hamming distance along each state transition between what we did observe and what we should observe if we followed that transition. And we do it again. And the next time we now have multiple ways to enter each node. All right. And that seems like a lot. So now we have not only going from all possible states to all possible states, but there are multiple ways to enter each node. But in any case, we just do it. So we have the top 0, 0 state, that stop line. We could go from there to the 0, 0. That's allowed. Remember, we should have seen a cross that. We should have seen a 0, 0. The true output state was a 0, 1, but the corrupted output state, the one we were testing, is 1, 1. So we see a Hamming distance of 1, so forth. We go all the way down. Maybe the interesting one is at this point, we should have been in the state 1, 1, transitioning up to state 0, 1. And that should be a 0, 1 output, but we observed a 1, 1 output, so the Hamming distance is 1. So we see as knowing everything that's the wrong Hamming distance, but it doesn't know it, right? That should have been the correct path, but the receiver doesn't know it. And then we follow this along. We calculate the Hamming distance every step along the way. All right. So that gives us all the Hamming distances between the observed sequence and what should have happened as outputs on that transition for all allowed state transitions. All right, so then the next question is, how do we figure out what the right path is? Well, we have all these distances, and what we're going to do is we're going to add them all up. We're going to take every possible path, which is a mess, right? This exponentially growing expansion of all possible paths. And we're going to find the path that has the lowest sum distance. All right. So that's just potentially takes a huge amount of memory and lots of calculations. But there are some tricks we can do to trim this a little bit. So, but let's go ahead and do this. So we now are going to follow each path. So along a allowed path, we've previously calculated the Hamming distance segment by segment of what we should see as output versus what we did. Additionally, we're going to, that S there is going to be the sum. We're going to follow that sum. So along the top path, we saw a Hamming distance of 2. So the sum Hamming distance is still, of course, 2 because there was no previous step. Hamming distance along the transition from state 0, 0 to state 1, 0, that Hamming distance is 0, so the sum is 0. All right, so we now are potentially in state 0, 0, or potentially state 1, 0. So if we basically follow the path, let's look at state 1, 0. The sum is 0 at this point. The distance, Hamming distance, if we go from 1, 0 to 0, 1 is 2. So the sum along that path is now 2. On the other hand, if we go from 1, 0 to 1, 1, the sum along that path is 0 because we had a Hamming distance of 0 plus a Hamming distance of 0. The sum is 0. We can follow other paths and the sums keep on climbing up. All right. So we've now gotten to the point where we have multiple paths into each of the nodes. What we observed is, and when we do this in this particular case, and hopefully for any code that's strong enough, is that the sum of one of the entries into a node is the sum Hamming distance is larger than the sum Hamming distance of the other entry into the node. Well, we will never care about the one with the larger sum because we will always follow the path of the lower sum, and the larger sum will never pick. So we can throw away that path, and you see the little red X there indicating that path that we're going to throw away. On each one of these cases, when we have multiple entries into these nodes, one of the paths we just throw away. So we could keep it, and it doesn't hurt us in some sense, some theoretical sense, but it's just memory that we don't want to have to deal with, and potential paths we don't have to think about because we know we'll never follow them. And we can do this for the next step as well. Once again, the next step, we have multiple sums, multiple paths coming into a particular vertex. We pick the one with the larger sum and throw it away. We only keep the ones that make sense with a lower sum Hamming distance. And that gets us to the final step, and we get to the final nodes. And then what we do is on all the input paths to each one of the nodes at the final stage, we check the sum Hamming distance coming into these nodes, and we see a sum of 3, a sum of 4, a sum of 1, sum of 3, sum of 4, sum of 2, sum of 5, and sum of 2. Well, the 1 is the one with the lowest sum Hamming distance, and we just follow it back, and that will give us the path, right? And if we know the path, remember each one of these state transitions of this path correspond to a particular input bit, then we can reconstruct what the corrected input sequence is. In this case, we decode 1, 1, 0, 0, 1. And we have successfully decoded and corrected for the error in the observed sequence. So a couple amusing things here. One, because of the way this code works, the information bits are not directly expressed in the output bits, the code bits that are sent. But the state transitions sort of know about what the input bit is. And there are like a gazillion possible state transitions. Well, not a gazillion. Each step along the way, there are as many as 8 different ways to get into each one of these 4 possible states, or 8 total getting into these 4 states. By taking a look at what's going on here and finding the lowest sum, we were able to find the path that corrects for the output bit error. And because the state transitions, there's a 1-to-1 correspondence between the state transition and the input bit, we were able to write down the input bits. So we did this under the assumption of hard decisions because it's easier for us to sort of write these things down and think about it. But it's worth noting that had we done this with likelihoods instead of Hamming distances, and then we could have multiplied the likelihoods together. Or if we liked, we could have done this with log likelihoods and could have summed the log likelihoods together. And this exact same approach would apply to doing soft decisions by summing up the log likelihoods as we move through this. And then now you know how to do soft decoding in some sense. And it would work the same. All right. So I think I said this before, there are some other codes like turbo codes that are built out of basically pulling together multiple convolutional codes. Convolutional codes been around for a while, but they're still actually used fairly commonly. And so this is a real coding approach that people use. I mean, people use block codes as well. Um, the A lot of modern coding has moved on to using LDPC and polar codes, but convolutional codes and sometimes block codes are still used. A more thorough discussion of this is beyond scope of what we're trying to do in this introduction to modern communications. But hopefully this will give you a flavor of how this works.